Welcome to Spring LIB.
Okay, in this problem we have electrons sent through an accelerator to 6 kilovolts. We have a screen 28 centimeters wide and 26 centimeters long, and we were asked what field is required to sweep the beam across the surface of the screen. So we can do this with a mixture of kinematics and energy. To start, we can say that the initial potential energy plus the initial kinetic energy equals final potential and final kinetic for the accelerated electrons. Assuming that the electrons have no kinetic energy to start, we can eliminate this from our equation, and we can also eliminate final potential. And so we're going to be left with a kinetic energy of 1/2 mv squared in the x direction equal the potential on the electrons field, E times V. So we can find the velocity in the x direction of these electrons after being accelerated through the accelerator to EV over m. So we can use this for later. Now, during the deflection of these electrons by the electric field, we could use some kinematics. The delta x of deflection should be equal to Vx times the time that it's in the field. Thus, t is equal to delta x over x velocity, or delta x times root m over 2ev. Okay. Now let's look at the force in the y direction due to the electric field. You can set it equal to E, the electron charge, times E, electric field, and then set that equal to MAY, mass times acceleration in the y direction, just using Newton's law. Thus, the acceleration in the y direction is going to be electron charge times the electric field over m. Thus, the y velocity, just quickly integrating, will be initial velocity plus acceleration, time in the field. If we assume it has no initial y velocity, as it starts to get deflected, this will simplify down to little e, big E, delta x over m, y velocity. So the next step is somewhat counterintuitive. We have to do a bit of geometry. We can say that the ratio of delta y for the screen and delta x for the screen is identical to the ratio of y velocity and x velocity. We could plug in some stuff we know. And do a bit of simplification. And we have a ratio of delta y and delta s of the screen compared to equal to these other quantities. So now we can solve for the electric field, it being equal to simply delta ys over delta xs mvx squared over E delta x in the field equals delta ys m 2ev over m delta xs E delta xf equals 2v delta ys over delta xs delta xf. We're at the delta x is the delta x of the screen, and this delta x is the delta x of the field. So here we can start plugging in our numbers. 2 times 6 to 10 to the 3 volts times 0.14 meters for delta y of the screen. We can plug in 0.34 meters for the delta x of the screen and 0.026 for delta x of the field meters. So our ultimate result will be 1.9 times 10 to the 5 volts per meter, and that's the electric field. Finally, you can say the total delta y of our deflected particle is just its initial velocity times field time plus 1/2 acceleration in the y direction times field time squared. This is just a kinematic equation for constant acceleration. We assume it has no initial velocity, so that goes away. And we're left with 1/2 little e big E over m delta x in the field over Vx squared, which will simplify down fairly nicely. Delta x field squared all over 2EV over m equals 5.4. Oh, sorry about that. A little noise outside the window. This all equals 5.4 times 10 to the negative 3 meters. Let's write that one more place. Delta y is equal to 5.4 times 10 to the negative 3 meters. And that's the amount of deflection. And that's it.